In this video, we are going to learn sampling distribution for sample mean. The mean of the sampling distribution of the sample mean is denoted as mu x bar. It is equal to the population mean. If we were to put all possible samples of a given sample size and calculate the sample means, then the average of all these possible sample means will come up to the population mean. This is why the mu x bar equals the population mean, mu. Remember that the mean is just a measure of center in a dataset, so it makes sense that the central value of all possible sample means would be the population mean. Some estimates will fall below the true parameter mu, and some will fall above it. Overall, there should be a concentration around mu. The standard deviation of the sampling distribution of the sample mean is denoted as sigma x bar. It equals to the sigma, which is the standard deviation of the population, divided by the square root of sample size n. The standard deviation of all possible sample proportions gives us the standard error of a sample. Remember that standard deviation tells us the average distance observations fall from the mean. It is definition we learned from Chapter 2. And the standard error for a sample tells us the average distance sample means fall from the true parameter mean. We use the standard error for estimators. And the sample mean and the sample standard deviation belong to estimators. The central limited theory is a very important theory. It tells us why we should use sample mean x bar. For a random sample of size n from population distribution having mean mu and the standard deviation sigma, then as the sample size increases, the sampling distribution of the sample mean x bar approaches approximately normal distribution. No matter the shape of the population distribution, if n is large enough, the shape of the sampling distribution approaches normal or bell-shaped. If the population distribution is normal distributed, then it doesn't matter the size of n. The sampling distribution is normally distributed. So pay attention, we did not use the word of approximate here. If you pay attention to the first sentence, we said no matter the shape of population distribution, if n is large enough, then the shape of the sample distribution approaches normal. It means it is not exactly normal. However, in the second sentence, we said if the population distribution is normally distributed, then it doesn't matter the size of n. The sampling distribution, I would say, is exactly normally distributed. If the population distribution is fairly normally distributed and n larger than 5, then the sampling distribution is normally distributed. If the population distribution is not normally distributed, or the distribution of the population is unknown, then n larger than 30, we have the sampling distribution is normally distributed. Pay attention to the third sentence. So it says the population distribution is fairly normal distributed. Then we do not need large of sample size. We do not need a large sample size to have a normally distributed sampling distribution. However, if the population distribution is not normally distributed, or the distribution of the population is unknown, we need a large sample size, n larger than 30, to have a normally distributed sampling distribution. This is figure 7.11 from page 317. In your lab this week, you are going to do a very similar simulation, or I say simulation study, to mimic this plot. For example, if the population distribution looks like this one, this is called uniform distribution. When n equals 2, the sampling distribution is called triangular distribution. However, when sample size increases from 2 to 5, the sampling distribution almost has a perfect bell-shape. When the population distribution is the exact normal distribution, when n equals 2, we have the sampling distribution is the exact normal distribution. If the population distribution is right skewed, when n equals 2, the sampling distribution has approximately bell-shaped, though not perfect. And this, as we can see, this sampling distribution is also right skewed. However, when n equals 30, which is fairly large, all sampling distribution have bell shape. In addition to knowing the shape of a sampling distribution, the variability decreases in the sampling distribution as n increases, which is implied by the formula here. The sigma of x bar equals to sigma divided by the square root of n. As n increases, this ratio decreases. Thus, the larger the n, the more precise the statistic is, and the closer the statistics fall to the population parameter it is estimating. In the plot, we can see that the sampling distribution of x bar is very narrow when n equals 30, and the sampling distribution is wide when n is small, such as 2. As we know, when the sampling distribution is narrower, it means the variance is smaller. Here are benefits of knowing the sampling distribution being normally distributed. First, we can determine the number of standard deviations away from the mean. A given sample mean is by using the z-score calculation with some changes in notation for sample means. If the z-score is greater than 3 standard deviation above the mean or less than 3 standard deviation below the mean, then the sample mean is considered as unusual. Here is the modified z-scores. So this is the sample mean. And this is the mean of sampling distribution. And this is the standard deviation of the sampling distribution. We can find the probability of any interval of sample means by finding the area under this normal curve. Step 1. Sketch your curve and sheet the area you are looking for. Step 2. Use the new formula to convert a value of x bar to a z-score. Step 3. Use the normal table to find the area to the left. Step 4. Find the shaded area. Pay attention that the x-axis no longer represents the different value x can take. Now the x-axis represents the different value x bar can take. Here is a summary of sampling distribution of sample means. It looks at all possible values you could get for the sample mean for a given sample size. It is centered at the mu x bar equals mu. Again, the mu x bar is the mean of a sampling distribution. The mu here is the mean of a population distribution. The average distance values the sample means from the population mean is sigma x bar. So this is the standard deviation of the sampling distribution. This one is standard deviation of the population distribution. The n here is sample size. This one is called the standard error. The more samples plot as n increases, the smaller the variability. The sampling distribution of sample mean is normally distributed if the population was normal to begin with, or for very large sample size, n larger than 30. This sentence is implied by the central limited theory. We can find the likelihood or the probability of getting a particular sample mean by using the following z-score formula and the normal table, just like we did in Chapter 6. So please pay attention to the similarity of the z-score we learned from Chapter 6. So here, again I will say the mu x bar is the mean of the sampling distribution. In Chapter 6, the mu here is the mean of the population distribution. And because for the sampling distribution, sigma x bar, we actually already have the square root of n contains in this sample. So that's why we do not need to divide the square root of n again. Some of you may have noticed the denominator actually equals to each other for left part and the right part.